Hello everyone, this is the first lesson recording for IM1 March 11, 2021. Let's start with some announcements. This Sunday is the Pi Day. That's March 14th, 2021. And to celebrate Pi Day, what you could do is go to Mod Pizza because 20% of any purchases will be donated to Prospect Literal Impact. So everybody wins here. You get some yummy pizza, and then 20% of the proceeds goes to Prospect Literal Impact. Okay, so we are going to start with a warm-up problem, and I would like you to take notes on this as well. So in your notebook, you're going to title it Caffeine Jolt, and this is a warm-up exercise. To feel awake to do your math homework, you drank a Starbucks mocha frappuccino at 7 p.m. It contains 100 milligrams of caffeine. Each hour, you lose 10% of caffeine in your body at the time. Alright, so the first question is, how much caffeine is in your body at 8 p.m.? Okay, so that's 1 hour after. What is the percentage, or how many milligrams of caffeine is in your body? Can you try to calculate that? So how would we do this? Well, we know that 10% is lost. So what I could do is find the 10% of 100 milligram. So 10% of 100 milligram is 10 milligram. That means I am going to lose 10 milligram in 1 hour. So I started off with 100. So what I'm going to do is I am going to take away 10 milligram. That's how much is lost. So I'm left with 90 milligram. So my answer at 8 p.m. I am going to have 90 milligrams of caffeine. Okay, then the next question is, how much caffeine is in your body at 9 p.m.? That's after 1 hour. So you might be thinking, oh, okay, so I'm just going to take another 10 milligram off from 90 milligrams, so I would have 90 or 80 milligrams. So 90 minus 10 is equal to 80. So this could be my thinking. However, is this true? Actually, not quite. Okay, so remember it's 10% of 90. So what is 10% of 90? So you currently have 90 and you need to, what is 10% of 90? That is going to be 9. So that means you started off with 90 milligrams. So you're going to take away 9. So you're going to have 81 milligram, not 80 milligram. Okay, so it's not as simple as, okay, I can just take 10 milligram off every hour. Okay, so then the next question is the model linear, exponential growth, or exponential decay? So what's happening each hour? The first hour, 10% was lost. The second hour, 9%, or first hour, 10 milligram was lost. The second hour, 9 milligram was lost. What do you think will be the third hour? It's not going to be 10 milligrams. It's not going to be 9 milligrams. It's going to be 10% of 81 milligrams. So that's going to be 8.1 milligram will be lost. Okay, and so on. So it is, the numbers are decreasing, but is it linear or exponential? It is exponential because we're not subtracting the same amount each time, but instead we are multiplying by some number. So it is exponential decay. Okay, so now let's think about an equation to represent the situation. So let X be the number of hours since drinking Frappuccino and Y be the amount of caffeine in your body. What would be the equation to represent this situation? A, B, C, D, or E? Please enter in private chat. And make sure you show all your work in getting your answer as well. Okay, so assuming you had an answer, let's see how we can figure this out. Okay, so let's just jot down what we know already. So when we are talking about time is equal to 0. Okay, when time was equal to 0, how much did we start off with? The initial value was 100 milligrams of caffeine. Okay, but after time is equal to 1, after 1 hour, we had 90 milligrams, and after 2 hours, we had 81 milligrams. That's what we figured out from the previous slide. And we said that in the third hour, what's going to happen is I'm going to subtract another 8.1 from this, and that's going to be, you take away 8.1 from this, and that's going to be 72.9 milligrams. So how would I model this? Okay, so what is happening here from this number to next number? What's going on? What should I be multiplying to 100 to get to 90? How do I do that? To figure out the number, you get whatever the number is and divide by the previous. So that's going to be 90 divided by 100, you're multiplying by, which is same as 0.9. Okay, and again, 81 divided by 90 is actually, because this is does also simplify to 0.9 and also 0.9 here. So you're multiplying by 0.9 each time. So this is an exponential decay function. Remember we said that the equation was going to be y is equal to a times b to the power of x, where a is the initial value. What is the initial value? That's going to be 100. What is the multiplier? We're multiplying by 0.9 to the power of x. X is the time. So the equation is going to be 100 times 0.9. That's a decimal here. And that is going to be D. Okay, I also want you to notice something. Okay, where did this 0.9 number come from? We were told that 10% is going to go away. How did that translate to 0.9? Well, 0.9, 10%, if I represent it in decimal, is same as 1, 0.1. Okay, it's 0.1. Now, what did we do to calculate this 90 milligrams? We calculated the 10% and then we subtracted it from the 100%. So we essentially are getting the 90% of the previous value. So 90% of 100 is 90. 90% of 90 is 81. 90% of 81 is 72.9, and so on. Okay, so 90% is really 100% take away 10%. So 90% is the number that we're multiplying by, and that's because we took away 10% from 100%, and that's where the 0.9 comes from. And we do that because we knew that it's exponential decay. And this is the slide from last lesson, so please do not take this down. But we said that the general equation is y is equal to a times b to the power of x, where b is the multiplier. Remember, the multiplier is going to be bigger than 1. If it's bigger than 1, then the numbers are going to get bigger and bigger and bigger, so it's going to be growth. Whereas if it's less than 1 but still bigger than 0, then the numbers are going to get smaller and smaller and smaller. So for the previous example, because the numbers are getting smaller, it has to be an exponential decay. That means we need to subtract the percentage from 1. So here is the thing. So when you're dealing with application problem with percentage exponential growth or percentage exponential decay, there are two different forms of the formula. So y is equal to a multiplied by 1 plus r to the power of t, and y is equal to a times 1 minus r to the power of t. So for exponential growth, it's going to be the left formula. For the exponential decay, it's going to be the right formula. What do different things mean? Y represents the final amount, and t represents the time, or it can be an x, it does not matter, but most often we are measuring the input as time. And a is the initial amount when t is equal to 0 or when x is equal to 0. And this r is the rate of growth. This is the percentage that you are given. Remember, when we had Katya's salary increase, we had 8% salary increase for Katya. So what did we multiply by? We first converted 8% into decimal, which is 0.08, plus 1, which is 1.08, and we multiplied that by 1.08 each time. Okay, so that was exponential growth. But for the previous example, the variables are the same. So, and you can tell that multiplier, it was bigger than 1. It was 1.08. That's why it was a growth. But for the cappuccino exercise we just did, the rate of growth, or this should be rate of decay, which was 10%, we're told that it's going to go down by 10%. You first need to convert that to decimal. Okay, so 10% converted to decimal will be 0.1. So you need to subtract 0.1 from 1. So 1 minus 0.1 is going to be 0.9, and that's what we were multiplying by. That was the multiplier. And again, because it was less than 1 but greater than 0, it created a exponential decay. And so this is what you're going to do whenever you have a percentage growth or percentage exponential decay problem. What you first need to do is determine, is it going to be growth or is it going to be decay? If it is growth, you're going to add that percentage. First you convert it to decimal and then add that to 1, and that's going to be the multiplier. If it is going to be decay, then you first convert that percentage into decimal and then subtract from 1. And so just the same way we did for Frappuccino. So that's going to be the general formula. With that, I would like you to try Desmos activity card number 1 and 2. Here we go. This is card number 1. This is a painting appreciation problem. The original value of a painting is $9,000. Let's pretend this painting was originally costing the owner $9,000, but the value increases by 7% each year. Because this is so special, each year the value of it is going to be increasing 7%. So first question is, does this model exponential growth or exponential decay? The values are going up each year, so that means it is going to be growth. Okay, then I submit this, and then it's going to ask you write an exponential growth function to model this situation. Okay, so to figure this out, we need to figure out what is the percentage, what is the initial value, and so on. So since this is exponential growth, we said it's going to be 1 plus r to the power of t. Okay, and what is the a? A is the initial value. A is 9,000. What is r? That's the 7%. But we need to convert that to decimal. What is 7% in decimal? That's going to be 0.07. So I need to add 0.07 here. So the final equation is going to be y is equal to a is 9,000 multiplied by 1 plus 0.07 is 1.07 to the power of t. That's my equation. Next, it's asking me to calculate the value of the painting in 5 years. That means I'm going to substitute x to be 5. When I substitute that in as expression, it actually even calculates it for me, and I submit it.